Welcome to the second part of Lecture 14. We're going to continue exactly where we stopped off last time and try to finish this up. All right, so we just ended with some common names for some carboxylic acids, and we're going to continue on from here. All right, so here's our familiar identify the longest chain, and then and change the ending, and then number the substituents, giving that functional group the position of number 1. So we're going to work on these. All right, so this A, I'm looking at this and I see 1, 2, 3, 4. I see 4 carbons. We have to start numbering these by the carbon where the functional group is. Okay, so this has to be carbon 1, 2, 3, 4. There are no substituents, so this would be butanoic acid. 4 carbons, butan, drop the E, oic acid. All right, pretty straightforward. B, it's benzoic acid, so it's benzene ring with the carboxylic acid group. So this has to be carbon 1. 2, 3 will give that chlorine the lower number. If I go around the other way, it'll have a higher number. So this should be 3-chloro benzoic acid. We don't have to say what number the functional group is on because it's understood that that would have the first number. All right. There we go. Butanoic acid is the basic chain, and that'll end there with no substituents. B, that's the basic group, but you have to add a substituent on. So 3 for the chlorine. There it is, 3-chlorobenzoic acid, our name. Carboxylic acids in metabolism. Glucose during glycolysis. Glycolysis is what happens when you are in anaerobic respiration. I'm sorry, well, you're breaking down glucose. That's what glycolysis is. And you end up with pyruvate as one of your breakdown products. But when you exercise, it's reduced to lactic acid because you don't have enough oxygen around. And lactic acid builds up in your in your muscles, and makes them sore. So when you've had a really hard workout and you're sore the next day, it's because you built up lactic acid. Pyruvic acid looks like a dicarboxylic acid to me, 2 carboxylic acid groups, and then the lactic acid is a common name for what would be, we start numbering from here, so it'd be 1, 2, 3. So this would be 2-hydroxypropanoic acid would be the IUPAC name for this lactic acid. When OH is just used as a substituent, we call it hydroxy. So again, this should be 2, if I were naming it by IUPAC standards, it should be 2-hydroxypropanoic acid. But the common name is lactic acid. In the citric acid cycle, also called the Krebs cycle, you take di and triboxylic acids, produces energy for cells. So carboxylic acid is very important. Here are some other products of the Krebs cycle or the citric acid cycle. All right, that's enough on carboxylic acids for now. Esters are like ketones. You make them by taking a carboxylic acid and an alcohol. So we will explore that some more as we go along. So you remember how ketones had the carbonyl group in between 2 R groups. So ketones were R carbonyl R prime. Well, an ester is R, carbonyl, and then O, and then the third, the second alkyl group. So it's very similar, except you got an extra oxygen in there. So what you do is, and we'll have it in a minute, this part right here came from the carboxylic acid, and this part right here came from the alcohol. So here, this is, this carboxylic acid part is right here on this ether, on this ester, sorry, and then the alcohol part came from there. Anyway, we'll see that again. Here it is right here. So you take many biological reactions are called hydrolysis reactions. I'm sorry, condensation reactions, because what you're doing is you're taking, what you're doing is you are taking water out. Condensation, water. Oops, you're taking all of this out. That's water, H2O. So before I was wrong about the oxygen coming from the carboxylic acid, that's coming from the alcohol. So here's the carboxylic acid part right here. Here's the alcohol part right here. All right, but we took water out. It's a condensate. So you're taking two molecules, sticking them together by removing a water molecule. Those are called condensation reactions. Butanoic acid reacts with methanol. So here's butanoic, 1, 2, 3, 4, butanoic acid, methanol, 1 carbon. So you're going to take this water molecule out right here and stick the two together to make an ester. So when we name esters, we are naming, the first part of the name comes from the alcohol. So again, this is the alcohol part, and that's methyl. So methyl, 1, 2, 3, 4, butanoate. So carboxylic acids were oic. Esters are going to be O8s. O8 ending. All right. So name of an ester has two words. The first word comes from the alkyl group that was part of the alcohol. So it is going to be the part where the oxygen is, the oxygen that's by itself, the oxygen that's not part of the carbonyl group. So this part right here came from the alcohol. So I'm going to say, and the alkyl group is methyl. So methyl, and then here's the carboxylic acid part right here. It has 2 carbons. So methyl, and then that's what gets the O8 ending. So it would be ethanoate, ethane for 2, drop the E, O8. So again, let's go through our endings. All alcohols, aldehydes, one ketones, oic acids, O8 esters. Hope I haven't left one out. Naming esters, alkyl, so what we've just talked about, right? So methyl ethanoate. Here are some esters in fruits and flavorings. They're in perfumes and in things that have odors to them. Esters are. So let's do a little practice on our naming. Here is the pen back. Here is the part next to the oxygen is the alcohol part. So this is propyl, propyl ethanoate. 1, 2, 3, 4, 5. Pentyl ethanoate. All right. 1, 2, 3, 4, 5, 6, 7, 8. So octyl for octane, octyl ethanoate. All right, we're going to get something besides ethanoate here. Here we go. 4 carbons. This comes first. Ethyl butanoate. 4 carbons on the acid part. 1, 2, 3, 4, 5. So pentyl, and then the carboxylic acid part, it has 4 carbons again, so butanoate. All right. Write the name of the carbon change from the alcohol as an alkyl group first, and then change the ic ending on the acid to 8. So it went from oic to O8. All right, so let's try this one. So here's the alcohol part. Remember, it's next to the oxygen. So, and the oxygen actually did come from the alcohol. So this is methyl, 1 carbon. And then 3 carbons, propanoate. So it was propanoic acid, propanoate. Methyl propanoate. So there's the methyl part, methyl propanoate. All right, moving away from those to a new group of substituents, or I'm sorry, functional groups, and these are going to contain nitrogen. So anytime you see that amine, amide, think nitrogen. Ammonia, it all comes from ammonia. So they can be very complex molecules. Lone pairs on nitrogen make the reactivity, that's the functional group. Functional group for an amine is going to be an NH, either NH2 is just amine, but I can take hydrogens off and replace them with R groups. So we'll talk about those. R in HR would be 1 hydrogen replaced with an alkyl group, or you can replace both hydrogens with R groups, and so on. So amines are derivatives of ammonia. Ammonia is NH3. Amides are like esters, and we'll see those in a bit. They have a carbonyl group and a nitrogen group. So instead of an OH, it has an NH. It has an amine group where, I'm sorry, they're like carboxylic acids. Instead of an OH here, it has an amine group. All right, so amines are derivatives of ammonia. There's ammonia. Take 1 hydrogen off, replace it with an alkyl group, and it's methylamine. This one, dimethylamine, trimethylamine. So you can actually take all the hydrogens off of ammonia and replace them with alkyl groups. Let's practice something we've talked about before. Looking at this nitrogen, it has 2 hydrogens on it. This is a primary amine. Remember, we talked about carbons being primary. In the notes, it talks about alcohols as being primary, secondary, or tertiary. That's very important for reactivity. This is primary. It's one other way of writing it. This one would be secondary. It only has 1 hydrogen on the nitrogen atom, and this has none, so this would be tertiary. Okay? If I take an NH2 group and stick it on a benzene ring, we've already seen that that's aniline. And if I put another substituent on, the NH2 group has to get the first carbon spot. Aniline is used to make fabric dyes, including indigo. Blue jeans are made from indigo. So here we have this is 1 of the hydrogens in ammonia being replaced with an ethyl group. So this should be ethylamine. Ethylamine. So this is an amine. Here, this is just aniline. Alkaloids are physiologically active nitrogen-containing compounds, anesthetics, antidepressants, and stimulants. Morphine and opium and so on. All of those things contain amines. Nicotine is a stimulant. Increases the level of adrenaline in the blood. It's essentially 2 rings. It's very addictive. This functional group here can be thought of as an amine, where that nitrogen has no hydrogens on it. So essentially, all 3 hydrogens have been replaced by alkyl groups. You can think of this part as an alkyl group, and this part as an alkyl group, and here's another one. So this is a tertiary amine here. And here, no hydrogens again, so it's very similar, certainly more complex than what we just looked at, but a very important compound given our habits. Caffeine, speaking of habits, is another it has a lot of nitrogens in it. It's a stimulant as well. It's found in coffee and tea and energy drinks and chocolate and so on. It's also addictive. Just try going off of caffeine and see if you don't get some good nice headaches. Morphine and codeine are painkillers found in the poppy plant. Codeine is used in prescription painkillers. It's structurally similar to morphine. Morphine is used to make heroin. It's just very strongly addictive, more so than even nicotine. And then OxyContin is a prescription drug that has physiological effects similar to those of heroin. Lot of drug abuse with OxyContin. Here are the structures. You see morphine and codeine up there at the top, and they do look very similar. In fact, I'm looking for, it's like those pictures, like what's different about these molecules, and the only thing that I can see that's different about morphine and codeine, of course you can get codeine in Tylenol 3. Morphine is a stronger drug, but look and the only thing I can see that's different between these two molecules is this OH group right here. You've taken the hydrogen off and you've replaced it with a methyl group. That is going to change its solubility. So essentially you've changed an alcohol into an ether group here. Looking at heroin and OxyContin. OxyContin I believe, is a synthesized drug. And it looks very similar to codeine. Probably start perhaps with some of those molecules, but there's an extra OH group here. And this OH group has been, essentially you're taking this double bond here, and that is now gone, and you're making a carbonyl group out of it. So it's a little bit different. Heroin over here, two ester groups. Ester. So they're very similar. All of these molecules are very similar to one another. That's why they're talking about them here. Amides, derivatives of carboxylic acid. So as I said before, take the OH off of carboxylic acid and replace it with an amine. Right here. So 2 carbons, ethanamide. This would be ethanoic acid. Now it's ethanamide. So we're going to drop the E off of the alkane name and add amide. So the reaction, we can get an amide from taking a carboxylic acid and ammonia. So that will take up our very familiar condensation reaction, or becoming familiar. You're taking water out and sticking 2 molecules together. You're taking water out, sticking 2 molecules together. So you're taking propanoic acid, putting an amine group on it. Becomes propanamide. Okay? Take propanoic acid, put methylamine on it, and now look how you name it. N-methyl propanamide. So it's saying with the nitrogen here that on the nitrogen I have a methyl, and then the other part of the amide is the propanamide. Okay, so we're going to take benzoic acid, and we're going to do a condensation reaction where we take water out. So this OH group will be gone, and this one of these hydrogens will be gone. It'll become 2. So drawing it, I'm just going to go ahead and draw it here, then we'll see how well I did. There's my ring, and here's my carboxylic acid part, and then I've stuck that on it. So benzamide, there we go. That one looks a lot better than the one I drew. And it's not going to tell us the name of that. So I'm taking benzoic acid here and sticking an amine group on, so it becomes butanamide. This would be propanamide. So there it is, propanamide. And this is going to end our lecture. So you got an extra 19, 20 minutes on this one. I think what I'll do is pause for a moment and find some practice so we can practice some of this. We'll go back to some of those same links. But here's a concept map that may help you organize some of this information. It's a lot of information here at the end. So I'm going to pause for just a moment and go get those links again, and then we'll do some practice to finish this off. All right, we did these quizzes, this first quiz on our last, in lecture 13. So let's go ahead and give quiz 2 a try and see if we can't do some of these. All right, I see an alkane here to start. And remember, I pointed out that the first two on this were alkanes. So I see cyclohexane, and I see 3 substituents on cyclohexane. So we're going to start numbering from, doesn't matter, as long as I start where one of the substituents is. So I've got a 1 and a 2. At position 1, I've got 2 methyl groups, so it's going to be dimethyl. And then I have a ethyl group at position 2. So since ethyl comes before methyl, I am going to say 2 ethyl, 1 dimethyl cyclohexane. And that's correct. So I started with the ring, because that's like my longest chain, and then I named the substituents that were off of the chain. We start numbering at, doesn't matter, at the first, at one of the substituents, such that the substituents, of course, have the lowest numbers. All right, so matching up the picture with the name, excuse me, I see an isopropyl group here, and a methyl group, and an ethyl group. And I see that the isopropyl is used. Cyclohexane is my parent chain. So if I start from the isopropyl group, I'd go 1, 2, 3, 4, which is probably fine. 1, 2, 3, 4. It's not going to matter. Let's go ahead and start with the ethyl. And it's ethyl, methyl, and an ethyl, and then isopropyl in alphabetical. Ethyl, and then isopropyl, and then methyl. So it should be 1 ethyl, 2 methyl, 4 isopropyl cyclohexane. Okay. All right, we have an alkene. Now, we did not do cis-trans, but let me just tell you that cis means that those 2 methyl groups are on the same side of the molecule of the double bond. Okay, so the first thing to look for is, as we've done before, is start at the end. Hexene, 1, 2, 3, 4, 5. That pretty much rules out the first, the top left one. Okay, so let me see if I can get my pen to work here. So that rules this one out. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This one's also ruled out as well. 1, 2, 3, 4, 5, 6. Okay, that one's good. And then 1, 2, 3, 4, 5. So really, this lower left one is the best. Dimethyl, but this is not cis, it's trans. So let me go back up to this one. 1, 2, 3, 4, 5, 6. My bad. This top one up here is not ruled out. This one is, because of the fact you don't have a 6-member ring. And this would be trans, 3, 4 dimethyl 3 hexene, 1, 2, 3. Double bond is on the 3rd carbon. So we built it out. 6 carbons is the longest chain. The ene ending implies the alkene. 3 tells me that that double bond is on the 3rd carbon. 1, 2, 3. But the difference between these two is something we did not talk about, and that's cis and trans. Cis, you're on the same side of the molecule, so these two methyl groups are on the same side in this molecule, and this molecule, they're on opposite sides, and that's what trans fats mean, that you have that kind of opposite side of, situation going on. So let me reset, and we're going to pick this as our answer. All right. All right, so build 9-bromo 5,6-dimethyl tridecane. Tridecane. 9-bromo 5,6-dimethyl tridecane. Okay. Not sure about that tri there. 1, 2, 3. Gotta have 10. It's just decane. I gotta have 10. So let's just do some. We'll start moving. Oops. Let's just start moving things into place and just see if we can't make any sense out of it. 9-bromo. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, tridecane. I guess that's what the tri is. It's for 13 carbons. 1, 2, 3, 4, 5. So I need this methyl group here. So I think I need to reset, and I need to put this one here, this one here. So those two methyl groups are next to one another, and then the bromine. All right. So 1, 2, 3, 4, 5, 6. Oops. Reset. One more time. 1, 2, 3. 1, 2, 3, 4, 5. That won't work. Reset. This one here. 1, 2, 1, 2, 3, 4, 5, 6. Oh, I think I gotta do it from the other end. Okay, so we put this here and reset. Okay, so this one goes here. 1, 2, 3, 4, 5. This one goes here. Yes. 1, 2, 3, 4, 5, 6. There we go. 1, 2, 3, 4, 5, 6. There's my two methyl groups. 7, 8, 9. There's my bromo. All right, it ends in cyclohexane, so that pretty much rules this one out because this is not cyclohexane, it's benzene. All right, 1-bromo, 4-ethyl, 2,2-dimethyl. Well, there's the bromo, there's the 2,2-dimethyl, and then the 4-ethyl. 1, 2, 3, 4. What about this one? 1, 2, 3, 4, 5. So that this one's ruled out because I can't get the 4-ethyl to work with this. Okay, if this is at position 2, that's at position 1, 3, 4, 5. So that won't work. It's not 4. Okay, this one, 1, 2, 3, 4, 5. So they're ruled out, but for the same as this one. So this is our correct one. It should be that one. All right. Okay, we've got a phenol group here, and then we have an NO2. So the phenol, the carbon that has the OH group would be carbon 1. So this is 1 and 2. So this should be 2-nitrophenol. 2-nitro. 2-nitrophenol. Alrighty. All right, we've seen this molecule before. I see toluene. I see toluene right, this whole thing right here. Whoop, let me start over. This right here is toluene, the benzene ring with the methyl group. And then I've got 3 nitro groups on it. So this is carbon 1, 2, start over. 1, 2, 3, 4, 5, 6. So 2, 4, 6, trinitro. When I draw with the pen, it puts figures in. 2, 4, 6, trinitro toluene, or TNT. All right, build para. Remember, para is when they're straight across from one another. Chloroaniline. So aniline is, the molecule is this whole part right here. This is aniline. Okay. So I've just got a chlorine in addition, and the P tells me it is opposite to the nitro group. I mean the amine group. There we go. To one of the gray hydrogens there. If it were ortho, I'd be putting the chlorine here. If it were meta, I'd put it here. Para, it's at the 1, 4, or opposite sides. 3-bromo 4-nitrotoluene. So toluene is the base. So that means that the CH3 group that makes it toluene on a benzene ring has to have position 1. So this is position 1. Oops. This is position 1, 2, 3, 4. 3. Nope, that wouldn't work. 1, 2, 3, 4. So this one is ruled out. All right, starting, this is not toluene. That's aniline. Here we go. 1, 2, 3, 4. That looks good. Let's look at this one. This is not toluene. So it has to be this one. And 1, 2, 3, 3-bromo, 4-nitro toluene. Ortho. Orthochlorophenol. So it's this. The basic group is this one. This is phenol. It has a chlorine on it, and it's telling me that it's ortho. So that means that this chlorine needs to be right here. Meta-nitrobenzoic acid. All right, why don't you give it a try? And then I'm going to put that nitro group where it needs to go. Meta. 1 carbon in between when it's meta. All right, I want to give this one a try. 6-methyl salicylic acid. Now, salicylic acid is what we're seeing here right now is toluene. So salicylic acid is a common name, I believe, for this carboxylic acid group, 6-methyl. Oh, I'm bad. This is the methyl group. So it's position 6. Salicylic acid is when these two functional groups are next to one another. So 1, 2, 3, 4, 5, 6. Salicylic acid is benzoic acid, which it would be this right here. So we're changing which benzene derivative. Okay, that's benzoic acid. You put another OH on it, makes it salicylic acid, and then methyl group at position 6. Yay! This is one of the ingredients for making aspirin. Some of these you can't. All right, we have a cyclic. Tell first of all, what is my functional group here? If you said ketone, you would be correct. So, I've got a cyclopentanone. All right, so that's my functional group. 1, 2, 3, 4, 5. I start from there. 1, 2, 3, 4. So I want to go in this direction. 2, 2, 3, 4. So this should be 2,4-dichloro, 2,4 Dichloropentanone, cyclo. Yay! Need a little boost after getting that first one wrong. Still can't figure it out. All right, Esther. Is that what you said? Great. Remember, we start with the with the alkyl group next to the oxygen because that came from the alcohol. So methyl propanoate. All right. All right, I see a aldehyde. It's not a ketone because you have to have R groups here, not H's. So this is one carbon. So this should be methanal. Yay! All right, what do we got here? Ketone? That oxygen there makes it not a ketone. This is another ester. So start here on the oxygen side. Propyl. 1, 2, 3, 4. And on the carboxylic acid part, I've got 2-methyl. So it's going to be propyl 2-methyl butanoate. It's not 3-methyl because it's 1, 2, 1, 2. It's on the second carbon. 2-methyl butyl propanoate, no, because the 8 ending, the propanoate, O8 ending, goes with the carboxylic acid and has 4 carbons. And there is no methyl group on this alkyl group as a substituent. So ruling out the other choices. All right, we got an amide here. Let's rule out because some of these aren't amides. All right, so this one right here, an amide is on the end like a carboxylic acid, and the NH group or the nitrogen group is on the end of the molecule. So now it says in methyl. That means that there's a methyl group attached to the nitrogen of the the ammonia derivative, the thing that makes it an amide. So this one is on the end and it has a methyl group. This nitrogen is on the end with the methyl group attached to the nitrogen. So that's a possibility. I'm ruling this one out because the nitrogen's in the correct place. This one is getting ruled out for the same reason. So it's going to be between this one or this one. Hexanamide. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. But this one has no carbonyl group, so it's ruled out. Yay! All right, whoa, this is an ester. So alcohol end, right here. Isopropyl benzenoate. The carboxylic acid side is benzoic acid, right here. All right, so isopropyl benzenoate. Isopropyl isopropyl Yay! Wasn't sure how to spell benzoate. All right. Okay. Propanone. That "one" ending tells me it's a ketone, so let's rule out those that are not ketones. This one here is not a ketone. This is not a ketone either. That carbonyl group's on the end. It's an aldehyde. This is an alcohol. So the only one that's even a ketone is this one, and 1, 2, 3, it's propanone, has 3 carbons. So that is reset, and that is my answer. Right? Okay, butyl propanoate. This is an ester, so let's rule out anything that's not an ester. Not an ester, not an ester. These two are. Butyl is on the oxygen end, so 1, 2, 3. 1, 2, 3, 4. Now this is, this is flipped, but that's okay. It can be flipped. All right. We're used to having the alcohol group on the right. It's on the left here. This one has a propyl group and the alcohol position, so it would be propyl. And then 1, 2, 3, 4. This would be propyl butanoate. This one is 1, 2, 3, 4. This one is butyl propanoate. 1, 2, 3. So reset, and that's fine. Okay. 5-chloro, 3-hydroxy, 2-heptanone. All right, so it's a ketone. The carbonyl is on the second carbon, so 1, 2, 3. I need to have the hydroxy on the third carbon, and I need to have the chloro on the fifth. So 1, 2, 3, 4, 5, 6, 7. That's why it's heptone, because it's a ketone. The carbonyl is on the second carbon. There's a hydroxy on the third and a chlorine on the fifth. Right. An alkene, and we do have a cis-trans situation here. This is why. This, I've got an ethyl group. I've got 2 ethyl groups. And they could either be on the same side of this double bond, or they could be on opposite sides. All right. So 1, 2, 3, 4. Not bad. 1, 2, 3, 4, 5, 6. We do not have cis-trans. Never mind. My longest chain. These alkenes can be confusing. 1, 2, 3, 4, 5, 6. And the reason they're drawn this way is because you want the functional group, which is the double bond, to be prominent. So we always draw alkenes this way and then put the rest of the stuff around, all right, where that double bond is. If this group here had not been bromine and had been another CH3 group, then I would have 2 substituents, 2 methyl groups, and if they were on the same side, it'd be cis. If they were on the opposite sides, they'd be trans. So we don't have that. So what we have is 1, 2, 3, 4, 5, 6. So this is going to end in hexene. Okay? That's how it's going to end. After I get rid of all my little from drawing. And on which carbon is the double bond on? 1, 2, 3. Doesn't matter which way I start. It's going to be 3-hexene. But before the 3-hexene, I have to put in the substituents. I've got a bromo and a methyl. So the bromo comes first. 1, 2, 3. 3 bromo. 4 methyl. 3 hexene. So, longest chain, 6 carbons. It has a double bond. That's the ene ending. The double bond has to be identified as to where it is, and it gets the lowest number, and that's carbon 3. At carbon 3, I also have a bromine group. It comes first because of alphabetization. And on carbon 4, I have a methyl group. What? 3 bromo. Just going to try something. Oh, it is cis, like I said at the beginning, because these 2 groups, even though it's part of the chain, are on the same side. Okay. All right, so what do we have here? We've got, I'm going to redraw this. Hopefully I can do it where it'll be easy to see. 1, 2, 3, 4, 5, 6. I'm going to draw it like we saw in the previous slide with that double bond prominent. Okay? And I've got a methyl group at the end. I've got, so here's a methyl group. 1, 2, 3. This carbon has a hydrogen on it. 1, 2, 3, 4. This carbon does not. I see that this methyl group and this methyl group, even though this one here is part of the chain, are on the same side, just like the previous example. So 1, 2, 3, 4, 5, 6. This should be 6 3-methyl 2-hexene, cis 3-methyl 2-hexene, right there. All right, we've gone through all 3 of these quizzes. You should feel very smart if you were able to stop and try some of these on your own. But you know what? The links are there and you can go back and try it yourself. All right, now let me go back and get one more link, and it's going to be this one. Remember this one from lecture 13? So we have other functional groups here. You could try some cycloalkanes, but that kind of went with lecture 13. So let's go to hydrocarbons and see what we have. See, they've got alkenes, alkynes. Don't worry about arenes, but you can do some practice. So what is this? Is this an alkane, an alkene, an alkyne? Arene, I believe, is another word for aromatic. So let's try that. That is a alkene. This is an alkane, all single bonds, and so on. So you see that there's a lot to be practiced with here. Let's go to oxygen and see what's there. Alcohols, phenols, ethers, carboxylic acids. So you can have lots of practice here. Nitrogen, you got some amines, anilines, amides. We didn't do nitriles. We didn't do anything with sulfur. And then halides. That's just let me show you. That's just chlorine, any of the halogens attached to an R group. So this is an interesting question. Look at the carbon atom. How many hydrogens does it have? Is it primary, secondary, or tertiary? It's secondary. What is this? The carbon that chlorine is attached to is a primary. All right, so some of that practice, but definitely go to the hydrocarbons and the oxygen and the nitrogen to get some more practice on naming and so on. All right, I am going to stop this lecture here. I believe it's gone on long enough, and that will wrap up.